Okay, so chapter 1.6. 1.6, instantaneous rate of change is where we are actually going to overlap between advanced functions and calculus. And this is essentially the heart of where you'll probably start calculus, because everything is about that instantaneous. We want to see the rate of change of a lot of things. And we start stretching it into a lot of different abstract ideas, but get the point. I hope you get the point. Here it is. A rock. This is very rough. You don't have to copy it down, okay? Because you're going to get a sheet very soon. You have a sheet in front of you. Okay. Average rate of change, as you know, you take two random points. Let's say that's a 1, and that's a 2, 3, 4, 5. Let's pretend we don't have any technology. All we know is a rock. How do we calculate the speed in which we're moving? Let's pretend this is d over d. How fast are we moving right at 3 seconds? Give me some ideas. Let's say you don't know tangentiality, okay? You only have average rate of change. What would be the most logical solution to use a rock if you want to know speed at 3? Will?
You go like the average speed between 2 and 4.
Sure. Get close as possible, right? We have a point at 2, and I'm sure we can figure out on the table, right? And information at 4, and we make a tangent. Oh, this is going to be hard. We make a secant. There it is. If we can calculate the slope between 2 and 4, we can sort of argue saying, hey, that's probably what the speed is at 3. What can we do better? Think about it. We'll have the right idea. 2 and 4 is pretty close to 3. So make a secant. Can we? What was that, Joseph? 2.9 and? 2. Oh, sorry. 1. What did I say? Oh, Yusuf, sorry. 2.9 and
3.1.
3.1. So if I made a secant with points 0.1 bigger and 0.1 smaller, can you argue that that's more accurate than 2 and 4? Well, then follow the pattern. Can we do better? 2.99 and 3.01. Okay, I was wondering if we were going to make a mistake. 3.01. Yeah, that's pretty close. That's a millisecond down and a millisecond up from 3. And we can argue it's pretty good. But can you make the argument that a millisecond in time is an instant in time? So here's a funny generalization. So now everyone's going to have a different interpretation. Here's where math gets a little wonky. And we need the entire math world to agree together. What will you define to be an instant in time? Now, what's fast enough for you to say that's an instant in time? Be wrong. I encourage you to be wrong, please. Huh? Well, that's impossible, right? We need something to work mathematically. And you know that as we get closer and closer and make that time interval smaller and smaller, we get more and more accurate. So what would you say is small enough for us to say instant? Everyone might have a different opinion. Okay. True. In a math context?
But in a math context, it has to be applied.
Well, debatable, but I get what you're saying, though. I get what you're saying. So in this context, in a situation where there doesn't seem to be any other story, right? What would be a number that would be generally agreed upon in the math world? And again, most likely you'll be wrong. It's actually not as small as you think. Zach? Okay. 10th decimal.
Not 10 decimal, like
10th place, so that's 1 decimal place.
yeah.
So 10 milliseconds, you're saying?
Yeah.
Oh, interesting. Okay. A little smaller than that. It is a little smaller, but you're closer. You're close. Is it like a unit? Yeah, yeah. It's a unit in time. Picosecond is smaller. So if you don't, people who don't know, there's meter, millimeter, micrometer, nanometer, and then picometer. So smaller than an. So that's 12 zeros or 11 zeros plus 1. Okay, that's too small. Mathematicians aren't going to make that many zeros. Too small. Smaller than that. Oh, sorry, nano. Oh, nano. No, bigger than that. 9 zeros is still too big. Does it? Close. 1 smaller than a milli. So mathematically, we just decided we can't even count 1 millisecond well as a human being. So an instant in time, we're gonna just generally, we're gonna accept that as 0.00. That's it. So we are going to make this interval an interval of 0.001, and that's enough for us to argue it's an instant in time. Congratulations, you're done 1.6. We just have to apply it now. So yeah, so these lessons, so the following that we're going to project on the board, we are going to experiment. We are not experiment. We are going to investigate how the numbers are going from, the intervals are going from 1 to 2, and then we don't like that, 1 to 1.5, and then we'll try the slope for 1 to 1.1, 1 to 1.01, and then 1 to 1.001. And you will start to see that the rate of change begins to be refined. It gets more accurate and more accurate and more accurate until you get to a point where it's like, I don't see any change, Mr. Kim. Why do I got to do this anymore? At that point, we can say we've made a proper conclusion, right? We've gotten close enough that we can assume that it's not going to change. And then we'll sketch it very quickly, answer a couple of questions, and then we're done today. And hopefully we'll go for our break a little bit later. Question? Mm-hmm.
3 seconds. How would you get an exact number for 2.999
Oh, the only way we would do that is not through a graph, but through an equation. So we'll see it here. All right. Everyone can turn to your sheet. The argument here, I sort of explained it on the sheet, but the argument, take a look at the equation that I present to you in the context of height and time. I ask you to calculate the change in y, so the change in height, the change in time, and then calculate the average rate of change. Try and fill that out while I get the technology set up. Okay, go for it. I'll give you a few minutes. Shouldn't take you too long. I give you an equation and I give you the time values. All right. Do you want to just wait on me? You just want to see me do it? It's gonna be the end of me. Oh, education needs money. You know what? Shall we just do it together? Would you rather? All right, I'll do a couple. All right. So again, assuming that we don't know what instantaneous rate of change, or in this case, IROC, is going to be, let's use our knowledge of just average rate of change for each one. If you see, I give you an equation up here, negative 4.9 t squared plus 25t. You might want to use a calculator, but delta H, what's the change in time? Well, it's going to be 1. It's going to be 1 second. What's the change in height? Okay, delta H of 2 is going to be negative 4.9, 2 squared, that's a 4, plus 25 times 2, that's 50. Negative 30, 16, 36, 19.6 plus 50. This is 30.4. Huh? Yeah. Yeah. I just did that in my head. You can do that in a calculator. You should have gotten that. So the average rate of change between 1 to 2 seconds is 30.4. Let's assume it's going to be meters per second. It's not very clear, is it? 30, that's a 30. Oh, I'm so stupid. I'm so stupid. I haven't calculated the other one. H of 1, negative 4.9 times 1 plus 25 times 1, that's 25. This is 20.1. So the difference of 30.4 minus 20.1 is 10.3. So there it is. My bad. Man, and this is being recorded too. I'm so embarrassed. Question?
Why'd you put 20 in?
Here?
Yeah, and then 10 up there.
It's a difference. I am subtracting.
Different? Oh my God.
Right? I'm doing remember, delta H over delta T. I'm doing slope. I'm looking to see what the instantaneous rate of change is at 1 second. So what we did was mathematically, it's like, okay, here's 1. Let's figure out the secant to 2. That's still too far. Let's try 1 to 1.5. That's too far. Let's try from 1 to 1.1. And let's try from 1 to 1.01. And then 1 to 1.001.
Well, that you get 1.
To get the instantaneous rate of change at 1. So this is an investigation. We're checking to see if this theory of making 2 points closer and closer together to become infinitely close is valid. Makes sense. And if we can use it for other situations. Okay. So there's that. Instead of 2 now, I'm going to try plugging in 1.5 because I want to know the interval between 1 to 1.5. So a question?
Yeah, I was just thinking for that first equation you're now erasing.
Yes.
Why was there 2 in the bracket in front of the H? I thought it was 1.
I did the one on the bottom. I did the.
Yeah. That's why I was lowering my hand step up.
Yeah. There you go. So now I'm checking to see what height would be at 1.5 seconds. So that's 1.5 squared times 2.5, 25 times 1.5, which I don't think I could do in my head. Disappointing, I'm sorry. 1.5 squared times 9 plus 25 times 1.5. Correct me if I'm wrong. The final answer appears to be 26.475. I'm just going to look for maybe 2 people to nod their heads. Yeah, thank you, Joseph. Yeah, Will, thank you. I'm going to subtract that. So the difference in time is 0.5 seconds, because 1 to 1.5. And the rate of change between those, that 0.5 second is 6.375.
Would we double that?
Exactly. So remember, slope is delta y divided by delta x. In other words, delta h, difference in height, divided by difference in time. That's the formula right here. So if I divide 6.375 divided by 0.5. That's essentially double. Oh, I typed in wrong. The rate of change is going to be 12.75 meters per second. Is it close? Yeah. Is it exactly the same? Absolutely not. But I can argue that we are actually getting more accurate this way. Yes, Sam. I took the first y value and I subtracted with the second y value. Because remember, I want to remind you, delta H means the second height minus the first height. Right? Yeah. Yes, Zach?
So
And then
in
come-
this specific situation, H is the H distance. And
Yes, H is the y value,
Okay.
right? So you can think about this as f of x is equal to negative 4.9 x squared plus 25x. Kinda? I will ask you to round if necessary. For now, let's just keep it because the whole point is I want you to see, yeah, I want you to see just how deeply we can get into this, okay? Or how accurate we have to be before we can accept it. So next one is the H of 1 is still the same. This time I'm going to test 1.1. So let's get more and more accurate. So the interval between 1 second and 1.1 second is 0.1. So what is the height at 1.1 second? That is negative 4.9, 1.1 squared plus 225 times 1.1. That is negative. Oops. 4.9 plus 25 times 1.1. That is positive 21.571. Confirmation? You got it? So I will subtract. The difference is 1.471, positive 1.471. And if I were to divide, because I'm looking for a rate of change, now it is 14.71 meters per second. So as we made the interval that much smaller, clearly our average from 1 to 2 seconds was a big underestimate. It wasn't accurate enough. So let's get closer. 1.01 is next. So the interval is 0.01. 1.01 is negative 4.9, 1.01 squared plus 25 times 1.01 squared times negative 4.9 plus 25 times 20.25151. Subtract it. 0.15151. If I get the slope, 15.151. So now this new number is actually really close to the previous one. I think we're getting somewhere. Very last one, people. Very last one. Let's see, 0.001 equals negative 4.9, 1.001 squared, 0.001. Oops, 4.9 times 25 times 0.001. 20.115195. Okay, so it's starting to get a little long, right? Yeah. I'm gonna keep everything just to prove a point, but yes, you can round if you like. So 15.1951. Really close. Close enough to the point where the difference is in the second decimal place. Does that matter if we are in space? Yes. Does that matter if we are on Earth? Not quite as much, right? So again, as Nathan was saying, context is probably really important, but I think we can start seeing that if we were to get any smaller than an interval of 0.001, we won't make that much of a difference. And so it's sort of universally accepted that for now, until you actually get into calculus, 0.001 is acceptable. But use your imagination. I keep saying mathematicians are the laziest people. Do we want to use 0.001 all the time? Sooner or later, someone came along and says, I don't have time for that. I'm going to invent a math that does this automatically for me. And that's calculus. Yeah. That's where calculus was sort of born. Like this was just too much calculation. You can think about it that way. Okay. Well, at least that's the intro to calculus, so to speak. Question?
Just a little lost on the first column, the height.
Mm-hmm.
Because it's just h2 minus h1. Like if I take the number that I 30.4 minus the number that I got, were you dividing or were you?
This one I was
For like
for here.
no, the column.
This one I had to subtract. It was h2 minus h1.
And h1 was
It was like 30 something. Oh, okay. No, I mean, yeah, correct me. I'm human, so I can make mistakes. All right. Part 2. Sketch the graph, a tangent at T1 and the secant specified in the chart above. This one's going to be a little bit annoying. I'm going to show you what that would look like. Why? Actually, I'm not too sure. I'm going to just draw it as a really rough parabola. So bear with me, okay? I might have to ask you for your numbers. Here we go, actually. Give me a second. Let me erase this. Oops. Leave this, and I can erase that. I don't want this. These are my X's and Y's. See your graph, don't worry too much. It's basically a rough graph. That's height. This is going to be time. How about we space out? We don't need much. So how about we space out 4 squares to be 1 second, 4 squares to be 2 seconds, 4 squares to be 3 seconds. This is in meters. It starts off at 0, 0. At 1 second, it goes to 30 point something. Okay. So that's 10, 10, 20. Oh, right. Sorry. So how about 10, 20, 30, 40, and so on and so forth. At 1 second, it was 10.20.1. At 2 seconds, it was 30.4. Yeah, 30.4. Right. It's an upside down parabola. Where is the? Okay, it's rough. It's rough. Let me just quickly calculate. 25 divided by 4.9. 2.55. So the vertex is somewhere here. Something like that. Okay, so this is the vertex. Yes.
How come time equals
The difference is at 10. We subtract it. The slope is 10. So I'll just use different colors. You don't have to work too hard for this. I mean, maybe I should have stretched this out. I will know for next class. I just did that for you. Yeah. I'm actually gonna make this bigger. Sorry, everyone. I know I'm going back and forth. You can keep your thing, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's make this. $10, $20, and then 1, 2, 3, 4, $30. That would be 25, and up there would be yeah. It's really hard to do this on the computer. I'm finding it challenging. So that would be 30. Okay. At 1 second, I had about 20-ish. At 2 seconds, I had about 30 something. And then 2.5 seconds, I know it's going to be a vertex, but that doesn't really matter to you right now. All that matters is that you know that this is a parabola. And it continues to go on like this. And then it goes back down. But anyway, the first secant that we drew, how about I draw it in red? It was from here to there. And that was a slope of 10. The next parabola, I'll use blue. It was from 1 to 1.5. That's right here, somewhere here. And then how about I use green? The next secant that we drew was from 1 to 1.1 second. It's going to be something like that. Which is a little, no, which is really hard to draw, but something like this. Okay. Oh, something like this. Okay. And then when we finally get to the tangent, I guess I'll draw it in pink. It's finally like it's tangential. It's really hard for me to draw it if I find, but I think you get what I'm trying to say. Let me do it one more time. Yeah, okay, in the final tangent, I'll make it a thicker line. There it is. Okay, so the final tangent, again, it started off a little bit, you know, it's steep enough, but as we got closer and closer to the time of 1, it became more and more accurate. It's just what I wanted to investigate. Any questions? No, right? Okay. I'm gonna have to cheat and we'll have to go for our walk a little bit later. On the back page is another question that gets you to try it without a graph. Like, what would you do if I only gave you a chart? Well, that's example 2. Example 1 is if I just give you a graph and you have to eyeball it, you will see that it's very inaccurate. And then we will do an actual version of it in example 3 when we come back from our walk. Once we go through this, you'll have close to an hour. We finish off what I call an in-class assignment. It's basically 2 questions that tests whether you can do instantaneous rate of change or IROC in 2 different equations. It's very straightforward. And I didn't want to make an assignment like hard because you only just saw it today. I think it's also fair that because it's slope, you can handle it. And 2, this forces you to take today's lesson seriously. All right. Questions? When we come back, we're going to do these 3 examples together, and then away you go. You can work in partners or if the people around you, whatever, and just hand it in. Okay. I will stop this here. And that's the end of our 1.6 lesson.